Hello, good afternoon, Jack. Good afternoon, Jesse. I will wait for a few, not minutes, let's say a minute or two, and I will start. In the meantime, you can see there is a list of steps we need to go through today, and two symbols I placed already into the schematic sheet to save some time. Okay, let's start, because why not? A few people is there or here, and I will, after that, after the recording is finished, I will edit the video and share it as a edited stream to save your time, so you can go watching anywhere you want and anytime you want. So, differential pairs in KiCAD. The most, I think, most frequently used differential pair is the USB lines. Differential pair for USB is the most used. The standard differential impedance for this differential pair is 90 ohms. And when we need to start, or when we start drawing the differential pair in KiCAD, we need to create and assign a net class for that, because otherwise, it's possible to do in standard like normal net class, but it's more convenient to keep the settings encapsulated in the net class. So to create a net class, we need to go to the PCB editor, into the board setup, and in the window of board setup there is net classes, and the default net class can be used for that. But for instance, you have design with Ethernet, USB, HDMI, and those differential pairs can be different. So I'm going to create a differential pair net class for 90 ohms. Let's say it will be called like this, and I don't care with the numbers so far, for now. So I'm going back to the schematics, and I need to create a label, to create a label and to assign a label to both tracks, both lines, because otherwise I cannot assign the net class. So label properties for the label is here. The KiCAD needs differential pair labels or differential pairs to be called with any string, but the string must end with plus, minus, or with P or N. So let's say we have, or for shorter version, DP, like data positive, and the net class will be our newly created DP90 ohm. So this is the first, and for second line, I just copy the label and rename the label to DN. So this is everything we need for schematics for now. The nets are named DP and DN, which is according to the KiCAD requirements. There is assigned net class. Now the numbers, the parameters of the differential pair. This is very important. And now we need to decide or determine what manufacturer you are going to use and how will look the PCB stackup. Let's say we choose this manufacturer. It's up to you, but this manufacturer offers very intuitive the capabilities sheet and very clear legible numbers. So let's go for the capabilities and PCB stackups. Highly recommend to use the 4-layer PCB stackup because for the optimal signal integrity, we need to place the differential pair as close as possible to the layer with the return path. And the standard single layer PCBs with 1.6 millimeters, it's not very good for that because the electric height is too high. We need to go closer to the signal layer. So the 4-layer stackup, the standard one, can work very well. So here are the numbers. The core, the electric height between the top and the inner layer is here, and the copper layer for inner and for outer layers are here. So let's get back to the KiCAD, to the PCB editor. And it's not necessary to place it here, but I just check if the numbers are correct in the physical stackup. For layer 1.65. Yes, the numbers are correct. So I place it correctly. So this will be our stackup. And now we need to go for the calculator for the impedance, or yeah, GLC PCB offers their own numbers, but I will show you the most general way. And I strongly recommend, or I use the Sierra Circuits impedance calculators. And we need to design the uncoated microstrip. The coated microstrip will be covered with some layer, but we just go with the uncoated one, and we need differential pair, no coplanar. This is what we need. So let's open it. We timed out, so this is something. I need to reload the calculator and log in again. So a few seconds. Now the calculator window is visible. I will change to millimeters because I can't think in mils. The electric height. This is the distance between the top layer and the first inner layer. It is 0.2104. So 0.2104 in millimeters. The electrical constant. The electrical constant for this material 7628 is in the table here, and the number is 4.4. So the electrical height is 4.4. Okay, and the trace width will be the number we are looking for. We need to place the trace separation. Let's start with 0.2, which is something close to the insulation distance, the minimal clearance of this class of PCBs, and the target differential impedance is 90. And now we need to calculate the trace width. So by pressing this button, we get 0.25, which is not bad, and I think we can go with those two numbers. So separation 0.2 and trace width 0.25. So let's get back to KiCAD, PCB editor, board setup, and we need to edit the net class, the clearance 0.2, track width 0.25, as I said, which is by accident the same as the normal default net class, but it's just the coincidence. So okay, now we need to check that the track is set to net class width, not my pre-selected width setup, just the net class. And we need to route the differential pair. The differential pair is routed by hitting the key number 6 or by choosing from this menu. So I chose, and here is the starting point in the USB Type-C footprint, and let's route something like this. Yeah, don't be scared if the track is not connected to the pads, because sometimes it happens. Now I can go to the closer to the footprint and make some small adjustments like this. So this is our newly routed differential pair. Now we need to check the length of the pair. For instance, you have some target length for the differential pair. The differential pair length can be checked and can be tuned. Let's check the length of the single tracks in the pair by pressing 7. The shorter or the inner track, and it's naturally shorter is 35.76. The outer is 37.24. Let's say we have some target length, differential pair length target, which is 40. So by tune length of the differential pair, by pressing 8, you need to select the pair. The pair is now selected, it's colored red. By pressing right mouse button, length tune settings, go there. And now there is like infinite tuned target length for now, but we need to set 40 as I said. So 40, and now you can see in the contextual mini window, the current length is now set to 40. So this is what we want. But as I said, when we tune length of differential or f of the differential pair, it means that we tune the length of the longer track of the pair. Let's see. We can inspect each track separately. So the inner one is still 38.5. and the longer one is 40. This is our target. So now we need to like tune the difference between length of those tracks. It's called skew. So we need to tune the skew of the tracks. It's possible by pressing 9 from this menu, tune skew, and we need to tune the skew on the shorter line. So we need to make the shorter line longer to be Yes, for length of 40, because the longer one has 40 millimeters, and we need to tune the shorter one to be 40 millimeters long as well. So I am going to tune the shorter track, and be aware, there are some segments of the track. There is one segment that can be placed the meander for skew tuning here, 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 and here. And when I click by the cursor, the segment is then selected as the segment for the skew tuning. So you will see. So now I click the segment. This is the segment which is selected. Just to check, here is the target skew is 0. This is fine because we need precisely the same length of the shorter track to be, the difference to be 0 between shorter and longer tracks. So now, without the meander, the skew is minus 1.49, which means that the shorter track is 1.5 millimeter shorter, and by placing the meander like this, the skew is 0. Now we can check the result by pressing 7, the inspect of the single track. The entire track is 40.00 millimeter long, and the shorter, this is not anymore shorter, both tracks are of the same, precisely same length, 40. And this is how it works. So I'm going to check your comments if there are some. Hello, Jenny. Hello, how are you? So, comments. No comments, no. There are comments, but no questions. So, I think we can be done, because I wanted this live stream to be as short as possible, and this is it. So just a summary. We created and assigned a net class for 90 ohm differential pair. We decided about the PCB manufacturer. We found the numbers or parameters of the PCB stackup. It means the thickness of the dielectric between the top and the first inner layer. We use the calculator for the impedance calculator to get the differential pair width and the differential pair gap. It means the distance between the tracks. Then we edited the net class for 90 ohms. We routed the pair PCB, the pair differential pair without any tuning. The difference was in a skew was about 1.5 millimeter, and the length was 38. We set the target length for differential pair as 40. So both tracks were tuned, and then we tuned the skew to be 0. So now our tracks of a differential pair are exactly and precisely tuned to the 0 skew, and the length of both tracks is 40. So this is it. So there is a question. I can read it here in the LinkedIn window. Let me see. Great demo matching the length. Hello, Joost. I'm glad you like it. Thank you for being here. What is the time difference tolerance for this USB interface? In the end, it's not about length, but about matching the timing. I don't know. I'm not so clever to answer this question. I don't know. You need to know. I don't know. Thank you for the question. So let's get back to the schematic. And I would at the 8th point. Don't overthink and overcomplicate. Okay, this is it. Thank you.